Occasionally we come across an integral that is very resistant to integrating in rectangular coordinates. And now we're going to look at how we can change to integrate in polar coordinates when it is more convenient. So this isn't a problem that makes existing questions harder. It's a tool that you can use to take a complicated integral and turn it into something easier. Let's look at, for example, we wanted to find the volume bounded by the curve z equals the square root of 9 minus x squared minus y squared, and above the the xy plane. So if we were to just go and set this integral up, first, if you look at the shadow of this region, the shadow of this region in xy will look like the disk centered at the origin of radius 3. So our region of integration on this would be, now the x value would go from -3 to 3. The y, given an x value, the y goes from the bottom curve up to the top curve. And then to figure out what that curve is, well, we know it's a circle of radius 3, so we've got x squared plus y squared equals 9. If you solve this for y, we get this as plus or minus the square root of 9 minus x squared. So that means the bottom branch is the negative, and the top branch is the positive. So those are our limits of integration. Negative square root of 9 minus x squared and positive square root of 9 minus x squared. And we're trying to find the volume, so that means the function we integrate is the square root of 9 minus x squared minus y squared. We integrate with respect to y and then with respect to x. So this integral, at first blush, looks like we have to do a trig sub, and then once we plug these quantities in, probably another trig sub that may be even worse than the first. So this is probably not the way to go on a problem like this. Instead, we're going to look at changing this to polar coordinates because their region is circular. That's the primary focus of this, and also the function is a function of x squared plus y squared, so that'll make things simplify a little bit further. But the main thing is we have a circular region centered at the origin, so we should think polar. So the idea here is we'll make the usual substitution. X equals r cosine theta, y equals r sine theta. And when we set up this integral in polar, we use this result that we're going to look at a little more detail in class, is that if we've got a function of x and y that we're integrating over some region, and this is in x and y coordinates, and we're integrating with respect to x and y, we can rewrite this as the double integral over a new region in r and theta coordinates. We're going to plug in, in other words, that'll change our limits of integration, is what it comes down to for this change on the outside. The x's will replace with r cosine theta, the y's will replace with r sine theta, and then there's this crucially important integrating factor we have here. Anytime you switch to polar, we've got to multiply the integrand by r, and then we've got our dr and our d theta in whichever order is more convenient. So let's actually see where this goes on this problem right here. First up, this integral, well, I'm going to be able to rewrite it as a double integral. If we look at the r's and the thetas on this, first off, the region of integration is an entire disk. So our angle, our theta, is going to go from theta equals 0 all the way around the circle to theta equals 2 pi. So we've got the full range of theta values from 0 to 2 pi. The r's range from the center of the circle at r equals 0 out to the edge of the circle at r equals 3. So those go from 0 to 3. So it's already looking much nicer. And now we're going to plug stuff into the integral. So we're going to replace the x with r cosine theta, replace the y with r sine theta. We simplify this and we get 9 minus r squared. So a slightly simpler integral than we had before. And also we've got this extra integrating factor of r. Okay, and now our inner integral was with respect to r, the outer integral was with respect to theta. So our integral looks a lot nicer. Our limits of integration are certainly better. And the inside function actually factors up as a function of r and theta. So we can use the box theorem to rewrite this as the integral from 0 to 2 pi of d theta times the integral from 0 to 3 of square root 9 minus r squared r dr. So now we have these two smaller integrals. The first one is straightforward. We integrate d theta, we get theta. Evaluated from 0 to 2 pi is 2 pi. The second one we can do by u sub. If you let u equal 9 minus r squared, then du is negative 2r dr. So what we can do here is multiply the inside of the integral by negative 2, and the outside will divide by negative 2. So it'll turn this into negative 1/2, the integral of u to the 1/2 du. So that made things much simpler. And our limits of integration have changed also. So u is 9 minus r squared. So if r is 0, if we look at our old limits, we're going to change them into new limits. If r is 0, we plug 0 in here, we get u is 9. And then at r equals 3, our upper limit of integration, if we plug in r equals 3 into our u sub, we get u equals 0. So we're integrating from 9 to 0. Okay, so the 1/2 and the 2 will cancel to give us negative pi. This integral right here, we can do the power rule, so we get u to the 3/2 times 2/3, evaluated from 9 to 0. We plug in our upper limit of integration, and it zeroes out. We plug in our lower limit of integration, we're subtracting pi times 2/3 times 9 to the 3/2. So those negatives will cancel out, giving us 2/3 pi. Now 9 to the 3/2, first we take the square root of 9, which is 3, and then we cube that, which is 27. And then finally the 3 and the 27 can reduce to just 9, so we get 18 pi for our volume. So when we integrate in polar coordinates, things really aren't that bad, provided the region is set up for it. So let's close by looking at some specific regions, just so you can get a feel for what is what in polar. So if your region of integration is an entire disk, then the r will go from 0 out to the outer radius. The theta will go from 0 to 2 pi. That's